Welcome to interference as seen in atomic spectroscopy. So, interference is any effect that alters the signal while analyte concentration is kept constant. We can remove the effect of the interference by removing the source of the interference, or by making our standards such that they also exhibit the same interference. Spectral interference is overlap of an analyte signal with signal due to other elements or molecules in the sample or due to the flame or furnace. So we can remove contributions from the flame or furnace using D2 or Zeeman background correction. Note that these two background correction techniques have been explained in the previous video. The best option when another element overlaps the analyte is to use another wavelength without interference. Alternately, a high-resolution spectrometer can be used to resolve closely spaced lines like this. In this case, we've got cadmium at 228.802 nanometers, and over here we've got arsenic at 228.812 nanometers, and you can see that they're well resolved here. Chemical interference is caused by anything in the sample that reduces the analyte atomization. For example, sulfate and phosphate will reduce the atomization of calcium. This is probably by formation of non-volatile salts. And we can reduce the chemical interference by adding a releasing agent. For example, EDTA will protect the calcium from sulfate and phosphate interference because the EDTA binds the calcium more strongly than does the sulfate and phosphate, but then is more easily atomized. Ionization interference occurs at low temperatures in alkali metals and at higher temperatures for other elements. And for any element, we can write an ionization reaction where we have the element in the gas phase being ionized to give us the ion plus a free electron, and we've got an equilibrium constant K is equal to the concentration of the metal ion, and we've got our equilibrium constant K is equal to the concentration of our ion times the concentration of the electron divided by the concentration of our neutral species. Alkali metals have low ionization energies, so they're going to ionize readily. For example, at 2450 Kelvin and 0.1 pascals, sodium is 5% ionized, whereas potassium is 33% ionized. And because ions have different energy levels than neutral atoms, then the analytical signal will decrease as the ionization increases. So we can use an ionization suppressor to reduce the extent of ionization. For example, adding cesium chloride will reduce the ionization of potassium because the cesium will ionize easier and will provide a high concentration of electrons. We can also compensate for many types of interference using a standard addition. And note the standard addition was covered back in section 5.3, so if you need to, pause the video now, go back and review that. So again here, we've got our standard curve in pure water, and then here we've got a standard curve in the aquarium water, where we're adding portions of standard to the aquarium water, and we already have some, in this case, strontium around to begin with, and we can then find the x-intercept, and that will be negative whatever our concentration was in our aquarium water. So by adding known quantities of analyte to the sample, any interfering species in the matrix will alter the observed response of the standard additions as well. So inductively coupled plasma eliminates many of the interferences that are seen in flame spectroscopy, and this is because the higher temperature will increase atomization. The longer residence time, which is about double, will increase the signal further, and chemical interference is generally negligible. The background emission is also generally low, where the sample emission is measured 15 to 35 millimeters above the load coil. The concentration of excited state atoms is higher in the center of the plasma than in the outer region, which means that the outer region is cooler, and so the relative population of excited atoms is lower. So, emission from the central region of a flame is absorbed in the outer region in self-absorption, and self-absorption increases with analyte concentration, which means that Beer's law will fail and the calibration curve will be nonlinear. With inductively coupled plasma, however, the temperature is more uniform throughout the plasma, and self-absorption is much less significant, which means calibration curves can be linear over 5 orders of magnitude. In flame and furnace instruments, the linearity only lasts about 2 orders of magnitude. If we couple mass spectrometry with our ICP, then the linear range is 8 orders of magnitude or so. We can also sample by laser ablation. So in laser ablation, a pulsed laser beam is focused onto a microscopic spot on a solid sample, that's here. This causes then particles, atoms, electrons, and ions to fly off the surface into the gas phase. Each pulse ablates just a few nanograms of material, so it's nearly non-destructive, and ablated material can then be drawn into the plasma and analyzed. Successive pulses of that laser light in the same spot can probe deeper and deeper in order to generate a plot of composition as a function of depth, and this is called depth profiling. So if laser absorption is used to sample and atomic emission is measured, then the technique is called laser-induced breakdown spectroscopy, or LIBS. Each laser pulse produces a plasma with a temperature of 10 to 20,000 Kelvin that only lasts a very short time. And initially, the emission from the superheated plasma is a continuum and thus contains little useful information for us. But the plasma expands supersonically and cools, and after a few microseconds then discrete atomic emission lines can be observed. So that was interference in atomic absorption.